Yes, so I'm going to talk about sediment-hosted mineral systems. And the clastic-dominated type that Joe talked about in the first talk are one of those type of mineral systems. So clastic-hosted mineral systems are one of our major sources of base metals, particularly lead, zinc, and copper. But not just those metals, there's also a load of subsidiary metals that you find associated with these deposits. Now this image is showing you, it's referred to as the wheel of metal companionability. The kind of 8 or 10 in the center are the main ore-forming minerals, and all the other elements you see floating around the outside, the closer they are to the center, the more likely they are to be found associated with that type of deposit. So for our kind of 3 sediment-hosted mineral systems, common byproducts are things like indium, and indium tin oxide is actually transparent, but it conducts electricity. So probably a lot of you right now are looking at some indium in an LCD screen or in your phone or so on. And another very important one is cobalt, and cobalt is used very widely in battery technologies. So just to kind of finish the motivation, obviously, as you would expect, there is very much increasing demand for a lot of these metals. So this is an example showing you the historical usage of copper through time over the last century, and you can see it steadily increases as we approach modern day. Now, a lot of people, both governments and mining companies and so on, worry about kind of forecasting future demand for these metals. This is showing you a relatively conservative estimate of future demand over the next 25 years. What you see is that we're predicted to need about as much metal, about as much copper as we've ever mined in human history to date. And that is why, whilst recycling plays a very important role in providing some of this necessary supply over the next few years, recycling alone is not sufficient, and there will be a need to extract more of these deposits through time. So how do the sediment-hosted deposits form? Well, again, Joe did a really nice job of kind of describing the mineral system. So I'm going to kind of summarize it very briefly. Essentially, we need a brine, a relatively salty brine, and the way we get that is we do large amounts of evaporation, concentrate those fluids down, and we can make them salty. What those brines do is they descend through the basin, and as they do so, they scavenge metals. In particular, they get lead out of feldspars, so out of either felsic volcanic rocks or arcosic sandstones, and they get copper and zinc out of mafic volcanic rocks. And after they scavenge those metals, they rise up along fluid pathways, which, again, as Joe mentioned, often seem to be along normal faults. And as they rise along those pathways, at some point they intersect a reducing conditions. So, for example, a black shale with lots of organic carbon. And as you cross from the oxidizing to reducing conditions, that causes the metals to precipitate out of these brines. Now, kind of one of the key parts of this is this fairly scary looking diagram, which is showing you the solubility of, in this case, zinc as a function of the temperature of the brine along the x-axis and the oxidation state of the brine on the y-axis. If you are anywhere in the upper right of these kind of thick black lines, that's where your brines can do their scavenging. They can hold a large amount of dissolved metal. This is where they do the scavenging. If you cross into the lower left sector, down in through here, that's where those brines will precipitate out those metals. So in our plastic-dominated systems, what's happening is we're crossing this precipitation horizon by transitioning from oxidizing conditions to reducing. And that's in contrast to magmatic mineral systems, such as the VMS deposits we just heard about, where you tend to cross down temperature down this way. So where are the deposits found? And the answer is in sedimentary basins. And we all know sedimentary basins cover very large amounts of the surface of the continents. But these deposits are only found in very specific places within those sedimentary basins. This is showing you all the major known base metal sediment-hosted deposits. The size of the symbol corresponds to the amount of metal in them, and the age of the symbol is given by the color. So you can see these things are up to about 2 billion years old. Now, clearly, they are dotted kind of fairly randomly around in the continental areas. And this has actually been one of the causes of a lot of the problem with these metal deposit types, which we don't really fully understand their geodynamic setting yet. We have lots of like hints of stories and stuff. But what that does is really hamper you if you want to go out into a kind of fresh continent and go, where should I start looking for these deposits? Until we understand that geodynamic setting better, it's very hard to kind of zoom in and begin looking in the right place. We can show that in really nicely in Australia. So We're going to zoom in on North Australia. I don't know why all my boxes have got white in them, so I'll just get rid of that. Go again. We're going to zoom in on North Australia with all these deposits up in down in through here, which is an area called the Carpenteria zinc belt. What I'm showing you here is a magnetic anomaly map in the area. And essentially what you're picking up is the kind of crustal geology in this area. So we have this very strong north-south grain in the kind of eastern area of the map. It gets a bit less obvious as you move up along the coast, but in through here, it's kind of running more kind of east-west. Now, the deposits very much cut across this crustal geology. So they clearly form some kind of arcuate distribution. They're kind of forming some kind of belt, but they cut across the geology, and that's a bit of a problem because traditionally people would like to use the geology to go and predict where to look for these deposits elsewhere. Now, where this kind of whole story really started is I had some friends working here in Australia, in Geoscience Australia, looking at this problem. And what they realized is that if you looked at the upper mantle beneath this area in seismic tomography, this is a surface wave velocity map, there appeared to be some relationship between the structures you see in seismic tomography and the distribution of these deposits. And that's not something you would necessarily expect, because no part of the kind of mineral system genesis I talked about with these fluids and these shallow sedimentary basin processes should apparently have anything to do with the upper mantle. So cutting through all of the kind of tedious science that I had to actually do as part of this project, we ended up with maps like this, which is showing you variations in the thickness of the lithosphere in this area. And so what you can see is that in the southwest, in the kind of blue colors, we have relatively thick cratonic style lithosphere, whereas in the kind of north and east areas, we have relatively thin, more regular continental lithosphere. And this black dashed line in through here corresponds with the 170 kilometer thickness contour. And it just happens to beautifully transition through all of these deposits in this area. But better than that, it doesn't just work in this area. So we can zoom out and look at Australia as a whole. If I now put all the deposits on in Australia, I'll flash them on and off. You can see, you can see that not only these deposits in the north are lining up with this contour, but also these large deposits in the south of Australia. And that includes, this is the Broken Hill mine, which is one of the world's largest lead mines. And this thing here is actually, it's actually a slightly different type of deposit called an IOCG. But this is the Olympic Dam mine. So this is the world's fourth largest copper deposit, world's largest uranium reserve, and it sits bang on this contour. We can zoom out again and do this on a global scale. And what we see is that this relationship holds true everywhere. Every single deposit that contains more than 10 million tons of metal is lining up on the boundary between thick and thin lithosphere, as imaged by a surface wave tomography model. And we can do statistical tests to look at the kind of robustness of the relationship. I'm actually not going to go into them because basically they all prove it to be a very strong and robust relationship. I'm going to go on to the more interesting question, which is why are these deposits forming in these settings? Well, if we go back to our mineral systems picture, I'm just going to move it around slightly. So I'm going to reflect it, and then I'm going to add on our new insight, which is that there's something going on with a step in the thickness of the lithosphere underneath these deposits. So what's kind of nice about this setting for forming these deposits? Well, first of all, we have very long-lived fault systems in these settings. As Joe mentioned, we often get these deposits forming during reactivation of these normal faults or rifting in the first place. And these faults are very long-lived in these basins on the edge of thick lithosphere. So, for example, this is showing you subsidence curve for the basin, the Carpenteria zinc belt basins. And you can see that there's this very kind of strong syn rift subsidence phase starting about 1.7 billion years ago, and then a relatively flat, like very thin post-rift thermal subsidence phase afterwards. If you look at the timing of the deposit formation throughout this period, you can see they, occurring at repeated intervals throughout this basin formation. So that's one thing that's nice. Another thing about it is this provides you the nice setting where we can get all our mineral systems ingredients together. So we have this kind of low elevation extensive platform where we can form large amounts of terrestrial oxidized sediments, and also get these evaporites to form. So we can do lots of evaporation, make those brines. Contrast that with what we have on the other side of the break, which is where we have our marine conditions, our restricted marine conditions, potentially with the euxinic water conditions, high organic carbon in the shales being laid down. This is also where you're more likely to get things like your mafic volcanics out, where you have thinner lithosphere, which is where you're going to scavenge your metals from. And add to that the geodynamic setting If you're on some kind of step in the lithosphere like this, perhaps there are things like edge-driven convection, shear-driven upwellings, and so on. And what that will do is bounce you back and forth between these two conditions and potentially intermingle the facies you need for your mineral systems in this setting. There's one problem with everything I just told you, and that it's equally true for any passive margin setting. There's nothing particularly relevant in this story to a cratonic rift. And so the question is, why are these things happening in basins that are forming in cratonic settings? And the honest answer is, I still don't necessarily 100% know the answer. We scratched our head about it for a long time and had to think about it. And one of the things we think is probably important is these fluids that are carrying the metals. So if we return to this diagram of the solubility brine solubility, the zinc in the brine, what we see is that you actually need your fluid to be, relatively speaking, not too hot if it is going to cross this interface between oxidizing and reducing conditions and precipitate its metals. It's no use coming down at really high temperature across this oxidation interface. You won't precipitate out those metals. So we need our brines to be relatively cool, on the order of 250 to maybe up to 300 degrees C. Well, I'm going to show you some very simple rift modeling. I'm sure most people here, this is bread and butter. So I just thought I'd include this just so everyone is on the same page. I'm going to show you very simple Mackenzie type rift models. So 1D rifting. It's going to be characterized by a beta factor, which is going to tell you something about the intensity of that rifting episode. And it's going to be characterized by a duration, a time window over which that rifting is going to occur.
Mark, you had 11 minutes now.
Perfect. Okay, thank you. So the column on the left, we're looking at a kind of regular continental lithosphere setup. So we have, roughly 30 kilometers of crust, around about 120 kilometers of lithosphere. This is the temperature structure, and we're going to rift it. So here it goes. During the syn rift phase, it's rifting and thinning. And what you're seeing is a spike in the heat flow, which is what this thing is here. And at the end of rifting, we go into this post-rift thermal substance phase. This is this classic kind of exponential decay type as the lithosphere boundary rebounds. On the bottom right area, you see the substance of the basin. So this is showing you the syn rift substance phase up until you reach the dashed line, followed by that post-rift thermal substance phase. This has all been sediment loaded, and I'm showing you the approximate evolution of the temperature profile within those sediments. And you can see that for this basin, this is a relatively extreme rift of regular sphere, beta of about 10. You end up with temperatures in the sediment pile that well exceed that solubility window threshold. So how do we stop that happening? Well, the really obvious thing is to turn down the beta factor, which you can do. So this is for a beta factor of 2. Now our basin nicely stays cooler. We don't get an excess of 300 degrees Celsius and so on. However, we end up with a much thinner basin. So the thickness of the basin is only about 2 kilometers at the end of syn rift phase in this model. And in that 2 kilometers, you need to get all your mineral systems ingredients intertwined. So what's different about rifting cratonic settings? There's 2 important differences. The first is, because lithosphere is so much thicker, the basal heat flow is lower. The second is, because the cratonic lithosphere is chemically depleted by melt extraction early in Earth's history, it's more buoyant than regular continental lithosphere. And what that means is, from an isostatic perspective, when you start to rift it during the syn rift phase, you get a more rapid substance rate in the basin. So I'll let this one go. You can see here we have the syn rift phase, so here's everything thinning. And then when we hit the dash line, we're going to transition to post-rift thermal substance. Again, this is a relatively extreme rift. This is a high beta factor rift. And what you can see is you end up with a very thick basin and loads of sediments, but it gets way too hot. Now, what's amazing is that when you turn down the beta factor in this setting, you hit this Goldilocks zone where you have large amounts of syn rift sediments. So you have a high chance of having all your mineral systems ingredients in that setting, but you can keep them relatively cool. And that is why we think that the very large sediment-hosted mineral systems are forming in these cratonic settings. So I can leave it there if we're kind of out of time, but or maybe I'll just very quickly show you 2 other things we learned in this study. So the first is, there's this ongoing question about how stable are the edges of thick cratonic lithosphere through time. And people have looked at this from many different perspectives, including a modeling perspective. And you can essentially make the steps in lithospheric thickness be destroyed very quickly by a convective system or stable through time by varying things like the depletion, the chemical depletion I already mentioned, or the viscosity of that cratonic material. Now, what we see in this kind of global database of sediment-hosted mineral systems is some of these transitions appear to have multiple phases of rift formation going on them. So, for example, if you look in this area up in through Russia, you have deposits that are around about 2 billion years old, deposits that are just under 1 billion years old, all sat on the present-day transition between thick and thin lithosphere. If we look at Canadian core area, where Joe was mentioning earlier, we see a similar story. So we have deposits that are 1.5 billion years old, deposits that are 1 billion years old, deposits that are 500 million years old, all sat in this setting. So these spaces, as a general rule of thumb, don't seem to be undergoing very rapid destruction over time. So we're looking at things more like the right-hand kind of setup in this picture. The other thing we learn is, and this is the initial motivation of this study, is we learn something about where to go and look for more of these deposits. So you'll notice, for example, looking at the Australian map, there's this very obvious kind of blank patch between these deposits in the north and these deposits in the south, in this red box in through here, where there are currently no known deposits. There's a very good reason for that, which is if you look at a geological map of Australia, this area is covered with a thin veneer of Cretaceous marine cover. So this has had later flooding across the top of it, and that's obscured the geology that would contain the deposits. So these maps now give us a new way to go and target where to look for these deposits, where they are potentially buried under cover. So with that, I will leave it there. And if there's time, I would love to take any questions. And thanks for listening.
Excellent, Mark. Very intriguing. There's one question by Bob Trumbull.
You can read it, but I just was wondering if there's if you have a comment about the observation here that you find these large deposits on, let's say, abrupt changes in lithospheric thickness, if I understood that correctly.
Yeah.
Is that in any way contradictory to Joe's idea that you have hyperextended margins? I would have maybe thought that with an abrupt lithospheric thickness step, the margin would not be hyperextended, it would be sort of more, let's say, cut off.
Yeah, no, I definitely, I agree. I think there are potentially some contradictions there. I think in particular, what temperature the fluids are that are doing the mineralization seems to be quite an important part of this story. Yeah, I think the only thing I would say is that I think, so for example, the deposits in Carpenteria, the thin lithosphere, you know, in the red kind of colors to the side of it, still has relatively thick crust beneath it. You know, we think it's still on the order of 20-25 kilometers under there. I don't know enough about the deposits themselves on a local scale, but I'm not sure if all of them are necessarily forming in the hyperextended setting. Maybe you know, there's a subset of them are or not. I honestly don't know the answer, and I don't have a good answer to your question. But yeah, I think there are some potential mismatches and things to work out here. Definitely.
Maybe it's a matter of scale. When you say abrupt, what sort of lateral distance are you talking about?
Yeah, so these maps are built from surface wave tomography models that have a typical horizontal resolution that's on the order of 200-250 kilometers. Depends a bit on the event and station spacing and so on. But for I very briefly showed you the distribution of the deposits with respect to that contour, and they are all within 200 kilometers. So they're all on this line within the resolution of the surface wave tomography.
I may add, Bob, to your question, from the modeling point of view, the rheology of the mantle lithosphere does not play such a big role in hyperextension. It's mostly the rheology of the crust. So the sharpness of the mantle lithosphere edge is not an indicator whether you get hyperextension or not. It's not really correlated, at least from what we see from the modeling.
Mm-hmm. Thank you.